In today's video, we're talking about robot spinner weapon systems, how to get from this to this, or even this.
This video is sponsored by PCBWay.
Hey there, this is Seth Schaefer from Team Just Cause Robotics, and in today's video, I would like to make a whole video and a website blog post to accompany it that delves into the specifics of how to design a spinning weapon system for your combat robot. This is a topic that I think there is an endless amount of depth that you can get into if you really want to, and I actually have 4 videos on my channel from several years ago going into this in excruciating and technical detail, but I wanted to make a shorter, more concise, more targeted video at a bit of a more basic level that'll help maybe 80 or 90% of people instead of just the 5% who want to learn absolutely everything and optimize the crap out of their system, so that anybody who's just getting into the sport can kind of understand what goes into picking the right motor, speed controller, weapon diameter, and speed, and everything about that stuff, and how those effects have different trade-offs that affect the rest of your design. So I'm going to try and keep this video down to about 15 minutes if I can, and basically just cover the very specifics of how to make this part of your robot do the thing you want it to do. Now, I'm not going to be covering anything about lifting arm weapons or wedges. This is just focusing on kinetic energy storing spinning weapons. And I'm not really going to talk about saws either, something that's meant for cutting. I'm really talking about something meant for kind of a single big impact, which is what most kinetic energy spinners are designed to do. So the way that I like to approach the spinner design, or the way that I'd at least recommend beginners to approach spinner design, is with a multi-step process. Step 1, you'll pick your weapon diameter, and oftentimes this is simply a matter of personal preference and what you think fits the aesthetic or the goal of your design. If you want a really huge weapon and that's what your entire robot's designed around, then put a huge weapon on there. If you want a really small diameter weapon that's going to spin super fast, like a small compact drum spinner or beater bar, then you can do that too. But when you're designing your robot, you're probably going to have most of the geometry of the bot designed around that specific diameter weapon, because you have to make sure that that weapon doesn't cut through your own robot's frame, so you've got to have clearance around it to make sure the rest of your components will actually fit. Next, you've got tip speed. Tip speed, again, is a bit of a personal preference thing, but there's a range that most people tend to fall within. That is between 200 miles an hour and 300 miles an hour, generally around the 250 mile an hour mark. Tip speed is literally how fast in linear speed the tip of the blade is going around in a circle. And it can be calculated by knowing the diameter and the RPM, or you can simply back calculate the RPM from a design tip speed, which I will cover in a minute. But essentially there is a nice little mathematical formula. Revolutions per minute times pi times the blade diameter is equal to your tip speed. It's because 1 rotation times pi is the circumference, and that's the distance that the blade tip travels in a circle per revolution, and then revolutions per minute gives you that distance divided by time, which is speed. And then you just have to convert in units to miles per hour or whatever you'd like. Higher tip speeds mean that your motor has to work harder to get up to speed, and it'll take longer to spin up your weapon to maximum speed. And the air resistance on a spinning mass or a spinning blade gets exponentially higher the faster your tip speed goes. This is why I recommend going higher than 300 miles an hour, because if you try to double your tip speed, you actually need about 8 times the power in your motor, battery, and speed controller to support that speed, and it gets crazy trying to find a component that can actually survive this. And honestly, with how fast robots are able to drive towards each other and how fast the blade is spinning, you also start to lose out on what's called bite, which is basically if you have the blade spinning too fast, then you only drive so slow, you only get the very tip of your blade to engage, whereas if it's spinning relatively slowly and you move quickly, you can get like the entire tooth of your blade to engage with the opponent, and this tends to allow you to rip off chunks and launch them into the ceiling and stuff like that. So a relatively slow tip speed plus a moderate to fast drivetrain will actually sometimes allow you to do a lot more damage than spinning your weapon a billion miles an hour. Part 3. This is where we're going to calculate what the ideal RPM of our weapon will be to achieve that tip speed, and from there we can start to talk a bit more about the relationship between your voltage and the kV to choose what kind of speed of a motor that you need. So first off, to calculate the RPM of the weapon you need for a given tip speed and weapon diameter, you can use a conversion factor that I developed, which is 336.14. So you just do tip speed in miles per hour times 336.14 divided by your blade diameter in inches, and that gives you the RPM of your spinner. So let's say your weapon diameter is 4 inches and your tip speed goal is 250 miles an hour. Then the ideal weapon RPM is 21,000 RPM. If you want to use an 8-inch diameter weapon, then you'd find that the ideal weapon RPM is half of that at 10,500 RPM. So now we need to take those numbers and do a bit more math to figure out what kV of a motor you want. The kV of a motor is simply the voltage constant, and this number is given for every brushless motor you might possibly buy, and it's simply how many RPM the motor will spin to at maximum speed per volt of battery voltage. So pretty much we're always using lithium polymer batteries in this sport because they're really energy dense, and lithium polymer batteries are 3.7 volts per cell. When you look at a lithium battery, you'll see a number followed by the letter S. That's how many cells are in series. So a 3-cell battery has 3 times 3.7 volts, which is 11.1 volts. 2-cell is 7.2 volts. 4-cell is 14.8 volts. Those 3 voltages will cover like 90+% of ant weights and beetle weights that you might find. So if our 4-inch weapon is spinning at 250 miles an hour and we need 21,000 RPM, well, now let's figure out what the ideal motor kV would be. We're going to need to know what the voltage is that we're using. So for the sake of example, let's say we're using a 3-cell battery, so 11.1 volts. So we just do 21,000 divided by 11.1 is 1,891 kV. 1891 kV for a 4-inch blade, and for an 8-inch it would be half that, or 946 kV. And that is the kV that you would need to spin your weapon hypothetically at exactly 250 miles an hour. So you don't need to get that exact kV. You're probably not going to find a motor labeled 946 kV. You might find a 900 or a 1000 or an 1100 or something, but you're not going to find 946. But that's okay because your tip speed doesn't have to be exactly 250 or 200 or whatever. So now we know what the ideal kV would be to get the speed that we want. Next, choosing your weapon motor. Now for picking weapon motors, I've divided this into 2 separate sections. You've got option A, which is the easier route, which is to use one of the hub motors that myself and a few other combat robot suppliers sell. These are designed to have a weapon direct driven on the motor. You can't use a normal motor for this in almost any use case that you might practically find for a beetle weight robot, simply because the bearings in the shaft of the motor aren't designed for that kind of force, and they will just break. For ant weights, you can sometimes get away with it, like I did on my 1-pound bot Sonic back there, but every time Sonic, which is a small vertical spinner, fought a horizontal spinner, the motor shaft would snap in half. So I developed a special ant weight hub motor, which should alleviate this problem. The RDY 5022 Mini is kind of designed for ant weights, but you could also use it on a beetle weight with a smallish weapon. Just expect the motor might not survive the biggest possible hits in the 3-pound class, and it also isn't going to be able to support as big and heavy of a weapon or as large a diameter of a weapon as my beetle weight hub motor, which is known as the 5536. Both of those dimensions are simply the diameter in millimeters and the width in millimeters. So the 5536 is 55 millimeters in diameter, 36 millimeters wide, and the 5022 is 50 millimeters in diameter roughly and 22 millimeters wide. So if you're choosing a hub motor, there's only a few kV options to choose from, but it's always fine to change that tip speed a little bit, I think. So with the RDY 5536 for beetle weights, right now I have 2 kV options, 1200 and 900, and for the mini version, the 5022, right now I have 2 kV options as well, which are 1100 and 1700, because those are meant for smaller diameter weapons that would spin faster. I have a handy tip speed and blade diameter chart that even looks at different voltages, so there is a link to that down below, and there will be in the blog post as well, and that'll basically let you look at a chart of, oh, this battery voltage with this diameter blade, I can get this tip speed with this kV of hub motor. And that'll make your choices a lot easier. Now we can move on to the much more complicated section, which is trying to do a belt drive system. If you're looking to make your own hub motor rather than buying one of my off-the-shelf ones because you think it's a bit expensive, you might be shocked when you start quoting with machine shops in the United States or places like Xometry and find that a single machined component could cost over $100. Thanks to our sponsor, PCBWay, this isn't a problem anymore, as you can get those parts machined overseas, still receive them in weeks, and get them to the tolerances that you need for your project. They'll work with quantities of just a single part up to hundreds of parts without an issue, and they offer CNC machining, 3D printing, casting, injection molding, and all sorts of fabrication methods to make your next project a possibility. Check them out at the link down below, and you can get a $5 credit off your next order. They've made some awesome parts for my bots and projects in the past, and I've got another part that they're making for me for my next bot, Shrapnel Mine, which will be competing on September 14th at NHRL. So make sure to stay tuned for that video when it comes out. So part 4B is figuring out your belt drive system. If you are trying to get a specific tip speed of a weapon, but your weapon is either really, really big or really, really small, and you want to use a relatively large or relatively small motor for it, you're probably not going to find the exact kV of motor that you want to drive that weapon. And like I said before, more importantly, if you stick your weapon blade right to your motor and then fight in a combat robot battle with it, you're probably just going to destroy your motor anyway. So generally speaking, people try to use a belt drive system when they're not using a hub motor that's either custom made or off the shelf, because hub motors can be incredibly durable by having huge bearings and a central shaft running through them that is meant to be a huge structural element of a robot, whereas an off-the-shelf motor is typically supported only at one side with a relatively thin shaft, and any load hung off the side of that one tiny support with that thin shaft is just going to snap as soon as there's a huge impact on it. A belt setup allows you to put a pulley with just a little bit of tension on that motor shaft going to a bigger pulley that typically will have a dead shaft and big bearings inside of it. And that way you've got your weapon hub being just a pulley basically with bearings pressed in and then a blade bolted onto that pulley. And that's exactly what we have in Division here. So here I've got my blade bolted onto a pulley, which is a 3D printed nylon pulley in this case. There's bearings inside of that and a big shoulder bolt shaft. Shoulder bolts are a fantastic way to make a dead shaft because they're very precise and designed to have bearings run on them, and they're readily available for just a few bucks a piece. And then I've got some 1/4 inch thick aluminum uprights supporting the weapon, and down here with these 4 bolt holes is where a weapon motor typically would mount if I hadn't removed it from this one, with a pulley just going right from here up to there. And I'll show that in the CAD view in a minute. So essentially what you're trying to do here is you can compensate for not having the exact right kV of motor by simply having the motor spin generally a lot faster than your weapon RPM and just have a smaller pulley on the motor and a bigger pulley on the weapon. And so now you can basically be free to use almost any motor and almost any voltage battery as long as you can compensate for that with the ratio between your big weapon pulley and small motor pulley. How exactly you determine that ratio is pretty straightforward now that we've already figured out what our ideal weapon RPM or ideal motor kV would be. So, like I said before, you've calculated your weapon RPM and you've basically figured out, oh, if I want to run a 4-cell battery, my RPM divided by 14.8 is what kV ideally I would have for my motor setup. But let's say you've decided that you want to use an 8-inch diameter blade with a 4-cell battery. You might find that with a 1-to-1 ratio, you would only need a 720 kV motor. But if you're not using a gigantic motor, you're usually not going to find a weapon motor that has that low of a kV. The larger the motors, typically the lower the kV range they're available in. But if you just use a motor that's 1440 kV instead, and you have a pulley that's twice as big on your weapon as it is on the motor, then all of a sudden you can get away using that same motor without your weapon speed being twice as fast. So that's really the principle of the ratio of your belt drive and how you would figure it out. You simply can look at the available motors that there are, see what the kV of the available motor is versus the ideal kV for a 1-to-1 direct drive setup, and then divide, your motor kV by your ideal kV, and that's the ratio of big to small pulley diameter or tooth count really that you need. And again, it doesn't have to be perfect because your tip speed doesn't need to be exactly 250 miles an hour. So if your ideal ratio is like 1.37425, but you can find a pulley that's 1.28 times the size of another pulley, that's perfectly fine. So for Division, this version of Division, this blade is a 7.5-inch diameter. I used a 4-cell battery in here, and I used an 1850 kV motor. with a 10-tooth pulley on the motor and a 30-tooth 3D printed pulley on the weapon. So every 3 times the motor would spin, this weapon would spin once. And so the weapon had a max speed of 9,126 RPM, even though the motor was spinning at 27,000 RPM. So this meant I had a tip speed of around 204 miles an hour, and that was plenty to do a ton of damage with such a big and heavy weapon. Here's a speed round of different tips for doing a belt ratio setup. So for ant weights, a 3mm pitch belt or S3M like you can find on Fingertech, or HTD 3mm, which is essentially the same thing. Those will work great. For beta weights, I would recommend using an XL belt. This is a 5mm pitch or 0.2 inch pitch, which is what I used on Division here, and that held up much better. People snap S3M belts all the time on beta weights and just don't even bother. I would recommend you buy an aluminum pulley with either a set screw or clamping hub to fix to your motor shaft, but you can usually get away with 3D printing the pulley on your weapon setup like I did just show you here. Nylon or super PLA are probably going to be good options for printed pulleys for a toothed belt setup. Because you're distributing the force over so many small teeth, you don't need a really strong metal pulley. But if you're running something like a V-belt setup where you're having friction drive everything, every time the weapon stops and the motor keeps spinning, it's going to basically burn up that pulley if it's made out of plastic, and it'll start to melt. So you do need to generally use metal pulleys if you're running V-belts instead of timing belts with teeth on them. You're going to need an exact center-to-center distance between your motor shaft and your weapon shaft, and to calculate that for given size pulleys, there's a bunch of online calculators. I like this one by BB-Man that I'll link below, but there's one from Fingertech for their size belts as well. The BB-Man calculator works for pretty much any timing belts that you could find. For V-belts, it's a little trickier. I would recommend that for V-belt, you have a slot where you would bolt in your motor instead of specific holes, so you can kind of slide it back to tension it more if you need it, or slide it forward to tension it less if you need that, since V-belts might stretch a little bit over time, and it's really hard to get the perfect center-to-center distance the first time. You can do that with timing belt setups as well, but I find if you go by these center-to-center calculators for timing belts, they are a lot more forgiving, because if you're within like the height of a tooth of the correct distance, the belt's going to transfer full torque no matter what. Don't forget, you need to assemble and fix your robot, so make sure you leave room not just for the motor and the pulleys, but the belt to get between them, and figure out how you're going to get the belt on and off easily when you need to swap it between matches. If, for instance, the belt breaks and you need to put on a new one, or it gets damaged or starts to wear. And also, for some designs, you might be able to get rid of the belt entirely and use gears to drive your weapon. I did this on my Antweight overhead spinner mini mulcher. You do need to have the motor really close to your weapon shaft to do this, so it doesn't work for all designs, and you're also transferring a lot more of the shock loads from every weapon hit into your motor. But if you have a beefy enough motor, or you try printing one of the gears in TPU or a more flexible material, you might be able to absorb some of that shock and have it work out for you anyway. Just be careful, because at really high RPMs, 3D printed gears will absolutely start to melt. And unlike timing belts, you're not distributing the force over a bunch of teeth, you're distributing the force over like 2 teeth. So you might end up needing to use metal gears. Speed controller sizing and choices. This again gets a little complicated only because manufacturers don't provide great data. All of the speed controllers meant for drones are rated for the type of load experienced in a drone, not the type of load experienced in a combat robot. You can buy a speed controller directly from justcauserobotics.com. 35 amp and 70 amp ones are offered right now, and I might have more options in the future. And I tell you right on the product pages for my hub motors, like the 5022 will almost always be fine with 35 amp, and the 5536 will almost always be fine with the 70 amp. So you can't really go wrong with those. If you use too large of a speed controller, all that means is you have a heavier speed controller than you need, but there's no real downside. But too small of a speed controller and it might blow up. You also make sure that your voltage that you're using is not higher than the rating on the speed controller. That's very important. If you plug something that is 20 volts, powering 20 volts into something that's rated for 15 volts, it will probably just immediately die. Motors, however, are basically copper coils and magnets. They do not instantaneously die if you give them a slightly higher voltage than they're rated for, but they will get a lot hotter than they're going to otherwise. So you can kind of get away with overvolting a motor, but don't try it with a speed controller. Last two topics I'm going to try and speed through a bit. What are bite and kinetic energy? So bite is literally, I already showed it before, but the faster your weapon is spinning and the faster you engage, the more your tooth can engage with the opponent. So the further down this tooth basically is more bite. So the faster your robot can drive and the slower your weapon is spinning, the more bite you get. And once you have a decent amount of bite, you can transfer a lot more energy into your opponent. But if you just spin your weapon faster, while you will have more kinetic energy stored, you might be taking such tiny little chips out of your opponent that you never get to huge impact that you're looking for. So basically, if you can get your robot to accelerate and drive really fast, you can spin your weapon faster and make better use of it. Otherwise, you might want to have a lower tip speed because you might not get full force out of your weapon hits if your weapon is spinning at umptillion miles an hour. There is a lot more detail on that in my spinner design video from 4 years ago. I'll link that down in the description. Kinetic energy, again, a lot more detail in my spinner design video from 4 years ago, linked down in the description. Kinetic energy is simply a factor of how much energy is stored in the blade as it is spinning, and that is determined not by the weight of the weapon, but by a function of the shape of the weapon known as the moment of inertia, or MOI. The MOI of a weapon is basically the average position of mass away from the center. So the larger the diameter and the more mass is on the outside, the more MOI that your blade will have. And this is basically mass times the radius squared. So a double the diameter weapon with the same mass, and like a ring that's the same thickness, for instance, could have 4 times as much MOI than one that's half the diameter and the same mass concentrated on the outside. Similarly, with kinetic energy, the speed is a squared term in the calculation. So it's 1/2 times the inertia times the RPM squared gives you the kinetic energy. So if you spin your weapon twice as fast, it gets 4 times as much kinetic energy. That said, again, spinning your weapon twice as fast has a lot of other trade-offs that comes with it. So you're generally going to want to be looking at that, 200 to 300 mile an hour tip speed mark. And instead of just increasing RPM to get more kinetic energy, you would rather optimize your weapon for more inertia by moving more mass to the outside. Like you can see here, you've got thin spokes and then more mass here, thin spokes and more mass here. This helps to get more inertia in the same weight of a weapon. But the trade-off is that, there's more likelihood that this will bend because you've just got these thin spokes here. I had lots of problems with that with subtraction. That blue and red blade you see all the way on the side there, that one bent as soon as it hit something. So the spokes on that were too thin to support that much power. And that is a optimization problem that you could write an entire PhD thesis on. All right, that's pretty much everything I wanted to cover in this video. I didn't cover nearly everything that anyone could ever want to know here. Again, there's 4 videos in a series I did years ago, 2 of which are just about the math and theory of the spinning weapon design, MOI, KE, and all of that stuff, and then figuring out motors and belt ratios and how to optimize your system in that regard. And then the other 2 are a computer-aided design tutorial in Fusion 360 on designing an asymmetric spinner that's flat, and then one on an asymmetric beater bar. So check those videos out if you want to learn a lot more. Make sure to check the blog post linked down below, because this video can only be uploaded once, but the blog post I can update periodically as new products come out, and if people come up with an innovative solution for making belt drives a lot easier, like I have with the hub motor for making direct drive easier, I'll be sure to mention that in an updated version of the article. All right, that's all I've got for you today. Thank you so much for watching. If you liked this, make sure to click like, and if you want to see more like this, make sure to subscribe and click the bell icon to get notified when my next video comes out. That's all I've got. Bye-bye.